This is Greg Troutwine with Marine Technology TV, and we are very pleased to be joined today by Christian Armstrong and Pim Kuus to discuss the Scottish Association of Marine Science, SAM's, research project to develop novel methods for tracking mobile bed forms in time series bathymetry data using Teledyne's Reson Seabat T50R multibeam echosounder. Christian and Pim, first of all, I welcome you to the program. And to start,
yeah, thank you very much for having us aboard, Greg. This is great. I guess I'll go first. So my name is Christian Armstrong. I'm a PhD candidate here at the University of the Highlands and Islands, based at the Scottish Association for Marine Science. And in essence, I guess I've been looking at how the seabed changes on the west coast of Scotland. So in short, I design, organize and implement bathymetric surveys looking at the seabed in what we call extreme tidal locations, basically to determine the relationship between tidal flows and seabed change.
Yeah, sure. So my name is Pim Kuus. I'm a product manager and senior hydrographer at Teledyne Marine. So Teledyne Marine is a big collection of companies, and within Teledyne Marine, I'm responsible for the E20 single beam, the Seabat multibeams, the Hydrosweep multibeams, and the Paris Sound sub-bottom profiler. So, and that involves the development of the product life cycle, what's happening in the near future, but also looking forward at how we will be doing our surveys in the years to come.
So Christian, to start us off, can you give us an overview of the SAM's project with insights on the impetus to conduct the project, why it was deemed important, and kind of a by the numbers look at the project using the metrics of your choice?
So the project really looks to repeatedly map the seabed of extreme tidal sites by collecting what they call time series bathymetry data, essentially resurveying the same area several times. Extreme in this context is defined by tidal flow speeds that exceed 3 meters per second, or around 6 knots. And so I'm particularly interested in quantifying how the seabed responds to these high energy environments over the course of months to years. Now these high energy seabed environments can be very dynamic, especially where the elevated flow speeds transport sediment, and as a result, these huge sedimentary structures are generated, not dissimilar to dunes that you might find in the desert. So they can be several meters high, hundreds of meters long, and they're also pretty mobile. They can migrate along the seafloor. So practically, these so-called bed forms are quite important, especially considering the increased interest in offshore development, especially in recent years. There's a need to better understand these high energy environments and how to build effectively and safely within them. And seabed instability induced by these mobile bed forms affects the seabed's suitability to construction. So in essence, by better understanding the nature of these mobile bed forms, we hope to improve the cost effectiveness of offshore construction.
I understand that the Falls of Laura, Loch Etive, was chosen as a test site. Can you discuss the specific physical characteristics of the site, with insights on why this site was chosen and what it was about this site that makes gathering information so difficult?
Yeah, of course. Yeah, it's a pretty awe-inspiring place, the Falls of Laura. It's at the mouth of Loch Etive. It's a common pronunciation, I guess, error. It's not really, but a loch for the international audience is a glacially over-deepened estuary. So although the glaciers in Scotland have long since disappeared, we still have the resulting fjordic environment. And so Loch Etive is about 150 meters deep, and it has these shallow, very narrow constrictions termed sills, again, resulting from past glacial activity. And the Falls of Laura occurs because of one of these sills and because of the shallowing. So the tidal flow becomes kind of restricted, and it's the difference in tidal height between the inner loch and the adjacent marine environment that causes the flow speeds to essentially increase, and they increase quite dramatically. We haven't got an absolute quantification of this, but the numerical simulations suggest that it's between 3 and 4 meters per second, so it's about 8 knots. It really does rip through there. So clearly it's an energetic site, and its location is very ideal for us because we are about 1 kilometer away here at SAMS. What's more is that in an initial survey in 2014, we identified some pretty peculiar bed forms that really attracted further investigation. So we chose this site as an ideal location for the development of novel methods, and we could develop these methods and then use them on other data sets. But it's not been without its challenges, and deploying the pole-mounted T50R, Reson Seabat T50R, meant that we could only effectively survey at slack water given these flow speeds in between the flood and the ebb tide. In the Falls of Laura, that lasts about an hour. So we get as much of the survey done within that hour window before the tide reverses and we get out of there, basically. So despite these sort of tidal dynamics, actually the biggest challenge came from the effects of rainfall. With Loch Etive having quite a large catchment area, essentially a lot of rainfall funnels into the inner loch and out through the Falls of Laura at the mouth. And when the fresh water meets the seawater, it becomes essentially layered due to the different densities. And this so-called stratification is quite dynamic with the vertical position of the interface between the two water densities, changing both spatially and temporally. So we had to also fit into that 30-minute slack water window numerous sound velocity profiles to correct for how the sound propagates from the sonar into the dynamically stratified water. So a challenging place to survey, but very worth it.
As I stated at the opening, and as you just confirmed, the Teledyne's Reson Seabat T50R multibeam echosounder was chosen for the study. Can you give us a little more insight on why specifically you saw that as the best suited for this task?
Yeah, absolutely. First, the T50R is just a remarkable piece of kit. It really is. Its compactness, firstly, was absolutely ideal. We needed something that could be mobilized extremely quickly, given our slack water window. And as I said, this system had to be fitted on the end of a pretty generic pole system used to mount other sonars. And we've had problems in the past with calculating the offsets for between the transmitter, the receiver, and the IMU and the antenna system. So with everything for the T50R, with everything being mounted first to a mounting plate, then being put onto the sonar pole or the pole system, a lot of the offsets were already pre-calculated. That made deployment incredibly efficient and meant that we could deploy it on vessels of opportunity. So it didn't matter which vessel we were deploying on, we could just turn up and go, essentially. And then there's the data quality. The 3D waterfall display for this system revealed the seabed pre-cleaned in incredible detail. And I really have to credit the high quality, not to me, because it was definitely not the surveyor that was at part for this. It was the software's automated functioning, so-called tracker functioning, where the sonar parameters are essentially tuned, the tuning that would normally be done by a professional surveyor, like the post length, is tuned autonomously. And that filters out any water column noise and the likes. So even an amateur like me can get it right, which is great. And lastly, I must give credit to also the what's called the normalized backscatter function. It is a really incredible software, advanced this piece. So when you're tuning all these parameters rather being tuned autonomously, the backscatter is also fed these tuning parameters, and it normalizes the backscatter so that we get a nice clean intensity data, a nice clean backscatter data, which you can visualize in real time without any spikes in the data or without any irregularities caused by this autonomous tuning. So yeah, a really incredibly efficient system that required very little cleaning. Cleaning took minutes instead of hours. So a very high quality system. Yeah.
So Pim, we're going to come over to you for a moment. Christian obviously gave us a very nice overview of the system that was used, but can you fill in some of the technology blanks? Specifically, can you give us an overview of the Teledyne Reson Seabat T50R technology and its capabilities?
So the work that Chris for his project had to do is something you do find a lot across different types of survey applications. So the nature of repetitive surveying. So if you think about dredging works, laying pipelines down, harbor surveys, it all has a repetitive character. And when you do those type of surveys, it's really important that ultimately when you look at the differences you really look at the changes in the seabed, not so much changes in the installation or systems. So like Chris was saying, setting it up, aligning it all, that's super important, and that's what this system is very suitable for. But then there's also the data quality. If you want to see really fine scale geological features, you need to have really small beam widths and lots of data points eventually. So that's what a system like a T50 can do. It runs between 4 and 200 kilohertz. So that's a quite wide range. So that means they can go really shallow to fairly deep. Gives them small beam widths, lots of beams, and then things like the normalized backscatter would be a great aid as well, coupled with the tracker, so that they don't need to worry about changing settings, and everything is just corrected for them in real time. And those are some things that are definitely unique to this multi-beam.
Can you discuss in a little more detail, what was it about this project specifically that was interesting and or challenging from your point of view?
Well, I would say again, it's that repetitive nature, because it's such a common thing that we see across all the different industries. And then there's also the backscatter element. So naturally, most people are interested in the seabed bathymetry. So we're talking about 3D points. There's more and more interest nowadays to also look at the backscatter, which gives you an idea of what type of sediment you're having, or if you want to see tracker. So those type of things, they came back in the work that Chris did, and that's of course very interesting for us to work together with SAMS on this type of stuff. And then there's also things like water column backscatter, which also gives you lots of information. So there's traditionally we see multi-beams as just a system that does X, Y, and Z, but it can provide much more different outputs, and this project definitely took the benefit of that. So
Christian and Pim, what do you consider to be the most interesting or unusual discoveries from this project?
There's been a fair few interesting discoveries from studying particularly the Falls of Laura. This site has had very, very little attention until recently, both academically and commercially. So it's an interesting, an incredibly exciting place to explore from the perspective of time series bathymetry. However, we did notice some pretty peculiar dynamics in the bed forms that were actually pretty inexplicable considering the tidal flows alone. So typically, a bit of context then, typically these mobile bed forms, they tend to migrate and maintain their wave properties, like, for example, their wavelength. However, in the last few years, there have been reports from around the world that have said that these wave properties have been observed to be dynamic. The wavelength changes and the amplitudes change if exposed to irregularities in the flow. For example, if the flow speed increases, you get more friction at the bed, increased sediment transport, and the wavelength stretches. So Falls of Laura, we observed this change, but only on one side of the system. So if you imagine the shallow sill kind of centrally, then the Falls of Laura occurring above the tidal system, flowing bidirectionally and reversing every 6 hours. You would kind of expect then that any flow changes would affect both the flood and ebb tides, and therefore influence both sides of the sill somewhat similarly. However, we kind of observed that the bed forms west of the sill, dominated by the ebbing flow, stretched, and the bed forms east didn't really resemble this change. So there was an asymmetry here that caused a lot of confusion, a bit of head scratching, and it wasn't until we considered the glacial past of the site that things started to come to light. So perhaps we thought maybe the flow system still possesses some of its riverine ancestry, if you like, predating the formation of the fjord. So we set about developing a numerical simulation, a model of the system, and using time series water level data, so how the water level changes, collected for a month, started to analyze what influenced the water levels within the loch specifically. And what we found was that the rainfall had a significant influence on the water level within the loch. That's something that we didn't conceive because we thought it was an estuarine environment. It's tidally dominated. That's not usually the case, but kind of like a river on flood, the rainfall affected the height of the water and therefore affected the tidal flows at the Falls of Laura. So the wavelength stretching that we observed in the bed forms west of the sill was actually found to coincide with the sediment transport increase in response to rainfall as predicted by the numerical simulation. Now this result is pretty fascinating because it means that even in a tidally dominated system, the meteorology can affect the seabed stability. And that has all kinds of implications for sill flows, tidally dominated fjords in other latitudes that have variable freshwater influx. How does that freshwater modulate that tidal operation, that tidal system? And how do things like heat, for example, get transferred into these regions, let's say at high latitudes where heat transfer is instrumental to like glacial melting, for example. So we kind of found a climate sort of based system or a climate based effect from the seabed and then worked our way back, which was quite an interesting way of investigating a system like this.
Yeah, so for us as a manufacturer, we're interested in enabling users to use our equipment and particularly, is high spec, high resolution equipment as easy as possible. We don't want you have to be a super user to use this type of kit. And like the automated features that Chris talked about before, those things do make it easier so that it enables more people to use our equipment to do these surveys, to gather this type of data, and come up with some really neat results. So to hear the kind of the ease of use that Chris and his team experienced, that's very good for us because that's really what we're trying to do here, is to make everything easier and simpler for our users.
Is the project now complete? And if so, what are the results or the results to date?
The project, well, my PhD has another 8 months to go, so we're in the sort of the home stretch now. The field work is all complete now, so that's a good sign. And I guess in addition to the results that I mentioned about the Falls of Laura, we also resurveyed another extreme tidal site, not been mentioned yet, called the Gulf of Corryvreckan. Now this is off the west coast of Scotland, between the Isles of Scarborough and Jura, and it's another extreme tidal site. It actually hosts the world's third largest whirlpool, which is quite an accolade. So we really tested the T50 here, as opposed to the relatively shallow 15 to 45 meter depths of the Falls of Laura. The Gulf of Corryvreckan is around 220 meters deep. So, and the currents are even faster, 5.5 to 6 meters per second on spring tides, which is an incredibly energetic place. And we were really excited by the Gulf of Corryvreckan, as we found in an initial survey in 2012, we found very peculiar sedimentary structures again. We talked about the wave properties before. Well, at the Gulf of Corryvreckan, we have wave interference patterns, which is something very peculiar for these sedimentary structures. So we want to know what would happen some 10 years later, and we expected, as you probably intuitively would, that it's a highly energetic, more energetic place than the Falls of Laura. The place is going to be completely different. Well, we went back and it is absolutely preserved 10 years later. There is no difference. It is exactly the same. You'd expect the bed forms to be more dynamic, but on the contrary, they are absolutely immobile by and large. So this is a bit of a mystery to us. We're still working this one out. And for now, all I can say is watch this space.